think it might have only just gone live. So I'll just reiterate a little bit. Crash course, fantastic stuff. We'll run through the content. We'll do a couple practice questions, and then we'll do a Kahoot with some more extra questions. All right, so let's dive straight into it. First up, we have DSP fundamentals. So we're looking at things like talking about the frequency domain, recalling Fourier, our sampling theorem, aliasing, bandpass, sampling, and quantization error. So this was covered within the first couple weeks. It is the first out of 6 topics. And the main things that we want to take note of are just going to be concerning how we convert from our standard Fourier given frequency domain to our digital frequency domain. Okay? So digital frequency is essentially just scaling the entire thing down by a factor of your sampling frequency, multiplying by 2 pi to put it in radians, and then making it periodic. Okay? So you'll note this little thing is periodic after the ends of pi. The little end bits get snipped off. All right, just recalling Fourier transform. Here it is. You won't have to use it too much because the main stuff that we're dealing with is digital signals. So that's just a little thing. We have our sampling theorem. We want to make sure that for an exact recovery of any signal, we want our sampling frequency to be at the very least 2 times the maximum frequency within that sample. All right? Next up, aliasing. Aliasing is essentially when we don't follow this sampling theorem rule, we end up having bits of our signal clipped off. Okay? Especially when we start chucking it into the digital frequency domain and analyzing, okay, what frequencies compose this signal. We lose data if the sampling frequency is not high enough. There is an exception to this rule, and that is given by our bandpass theorem. Essentially, we can recenter our analysis about some non-zero frequency, given that the band that we are sampling at is, it has fs, our sampling frequency, equal to at least 2 times its bandwidth. The easiest way to think about this is usually we get to sample some kind of signal between 0 and 2 pi, like this. This is how our digital frequency analyzing would go. In this case, however, we don't want this thing, and we're instead going to think about a much greater set of things to consider. Okay, and in this case, it has to be multiples of our bandwidth. Okay, so in this case, bandwidth two times bandwidth equals fs. So you have to have a multiple of your bandwidth as the upper end for where you are analyzing. And so you can shift your analysis up by a multiple of pi times whatever number you want, okay? And that allows us to recover whatever signal we want in this kind of region. So that's all the bandpass stuff really is. Just a reminder, to avoid aliasing, we need to make sure that the maximum frequency that we are trying to capture is an integer multiple of your bandwidth, where bandwidth is a half of your sampling frequency. All right, moving forwards, a little callback to quantization error. It is essentially given by this formula right here, and it is provided in decibels. The way this comes about is we're talking about averaged error, just a little extra things. SQ&R is just signal equal to quantization noise power ratio. So this is just the error you get when you are converting an analog signal to a digital signal, okay, where you have to chuck it into discrete levels. And so when we go about this, the average error is given by your sum over 12. But we don't need to think too much about the probability density and stuff that goes into this calculation. We just really need this form. We define PS as your average power. We define R as your dynamic range. So this would be the maximum and minimum voltages you're accommodating within your your analog sampling region. L denotes the number of levels in your quantizer. And yeah, so most primarily we're talking about using this with a sinusoid. So sinusoid A given as the amplitude gives us the average power of A squared on 2, which kind of relates back to RMS, but anyways, R is given as 2A because we have to go up to A and minus A, and B we can use as the number of bits within a quantizer, so we know the number of levels to be 2 to the power of B, giving us the standard form of SQ and R being approximately equal to 1.76 plus 6.02 times B, where B is the number of bits in your quantizer in decibels. Fantastic. All right. If you guys have any questions, just please raise them at any time. In the meantime, we'll get cracking. So now we have the second section. This is for discrete time systems. Just a little overview. We have block diagrams using multipliers, summers, and delays. Delays can have two different notations so far. And we have a couple classifications for our discrete time systems. So first things first, we have static systems, otherwise called memoryless. That is where it is only a function of a present state. Okay? Next up, we have time invariant systems, which are, in other words, my transfer function that I'm dealing with doesn't change. Okay? It doesn't change with respect to time. Sometimes you might see, okay, let's give an example. If yn equals to n xn, then at certain times, I'm not going to get a signal. And so it actually changes with respect to time. It is time variant because this n varies with time. Okay? So that's one thing we have to be mindful of. Next up, we have linear systems. So linear systems simply obey the law of linearity. We're able to apply that however we see fit. And it will come up multiple times, but this will just be the quick overview of, okay, here's what linearity means. Yippee. Next up, we've got causal systems. Causal systems just means we're not looking into the future. We're actually able to operate on stuff in real time. And yeah, stable systems, everything is bounded. All of your inputs exist within some certain bound. It does not go up exponentially. Yeah. All right. Just a little bonus note. We'll typically be working with linear time invariant systems. These systems work with convolutions, and we treat them as our FIR and IIR filters. All right. So our biggest tool at hand is going to be our Z transform. Z transform is just given by attaching a Z to the minus n to every bit of your signal that you're using, and that acts as a delay counter. So this essentially turns any signal into a summation of delays. Okay, so you're just considering xk, n minus k as, consider x n equals sum of deltas. You're just attaching z to all your deltas, okay? And that comes a little bit more useful when we start talking about convolution, because it is just about mixed sums. Anyways, apart from that, we have linearity once again. We're not going to show you the rule, as we just said. It's the same for everything that uses that word. We have shifting within the Z domain, where it is just applying a delay to your certain values. We have differentiation, and we have convolution. An important note is that across pretty much all of our systems, we have convolution always maps to a multiplication within a greater domain. So in the time domain, we have a convolution, and in the Z domain, we have a multiplication. And in some instances, it might be vice versa. Anyways, this brings us to pole zero descriptions of our signals and their relative frequency responses. This is how we notate them, and we can just keep on moving. Discrete time Fourier transform. So, in this course, we recognize the Fourier transform, we recognize the discrete time Fourier transform, and the discrete Fourier transform. And the main differences between these transforms is just which parts where are discrete. Okay? So we understand that within the Fourier transform, we're just going from a continuous function to another continuous function in the frequency domain. However, into this discrete time Fourier transform, we're moving from discrete time still to continuous frequency. Okay? And so, where we would typically have an integral, we now have a sum. All right. Inverses exist very similarly to how they are in the Fourier transform, but let's just get into a couple of its properties. We got the linearity factor, time shifting factor, frequency shifting, convolution, and Parsifal's theorem. So most of these are very similar. A time shift, which is just a delay, can be thought of as the exact same thing in the Z transform, where we apply Z to the minus k, we apply Z to the minus j theta k. Yeah. Frequency shifting now exists, so we can actually shift the frequencies that we're analyzing by a certain factor. And convolution, always the same, but in this instance, it also works in the other direction. We have that a multiplication within the time domain also maps to a convolution in the frequency domain, which is rather interesting, especially just given the fact that multiplications in terms of time, we're just thinking about element-wise multiplication. So if I have 1, 1, 2, 3, 4, 5, then let's just think, I'm thinking of these as my systems going down in terms of n. This would give me just 2, 6, 20. Okay? Nothing too daunting. And finally, Parsifal's theorem. So Parsifal's theorem, it can be thought of as a conservation of energy type thing, where we're thinking about, okay, what is the total energy of my signal? But yeah, there's not too much we need to think about in terms of it here. It might come up within a question or two, especially within the tutorial questions. But yeah, it's just something fancy and nice to know. Next up, discrete Fourier transform. For this little thing, we have to think mostly about the fact that we're moving into a discrete frequency domain, okay? And so the resolution of our frequencies now is purely dependent on the resolution within the time domain. In other words, the number of samples we have. So, just a little definition bit. Instead of using theta, we're now defining it as another just kind of rotation between 0 and 2 pi, but just for our number of samples. We note that the discrete Fourier transform is periodic about n, which allows us to do this full rotation and skip out on a funky integral. Okay, so this brings us to the fact that, okay, given that we're only talking about n samples, the discrete Fourier transform has conjugate symmetry. So what that means that whenever I perform my discrete Fourier transform, I get a sequence of values that are conjugates of its opposite value. So if I had 1, 2, 7 minus j, 3, and I say 3 was the midpoint, then as I have conjugate symmetry, I would get j, 7, 2, 1 on the end. All right? Fantastic stuff. And once again, we see Parsifal's theorem here. It is of a very similar form. We just note that the 2 pi is replaced with an n, and that is just about it. All right. That is section 2 down, onto section number 3. So we have digital filter fundamentals. Just as a little reminder, we understand that the digital filter yn, we're usually talking about time invariant systems. And this is how we will formally characterize such systems, the way we define an output at a specific time instant as a function of previous inputs and outputs. All right. All we know is that for FIR, since there's no infinite response, it's not as though we're going to use infinite coefficients for our x values, so we'll just form some kind of repetition with y. So FIR means that your y coefficients go to 0. This brings about phase delay, group delay, linear phase filters, and then certain filter structures. Okay? So for phase delays, we're only talking about at specific frequencies. What is the delay we observe within that region? So it's just given by this little formula. We don't use it too much. We are more concerned about group delay, but phase delay gives us a bit of insight into how much time each individual signal is going to be missing out on. Okay? Which can be very helpful when you just want to quantify potentially some kind of k value if a system has been delayed by a certain amount. This helps you calculate it. All right. Next up, we have group delays, which just supplies a rate of change of the phase delay. Okay? Fantastic. So, I guess this brings us about to linear phase filters, where they have a couple of interesting properties. Typically, we find b either equals 0 or pi on 2. But the main thing we want to talk about is going to be this expression right here. So, by having our group delay essentially just being a constant, what we observe, especially in the case of b being equal to 0, you get a function of phi of theta looking very much like some manner of straight line. Okay? And if it is a straight line, what we can observe is by dividing it by some value theta, the value theta being a theta here, you get a constant number. Now, what this implies is that your delay is proportional to your frequency, and so the delay we're talking about is by some constant time factor. Okay? So you can tell just by thinking, okay, if I have a high frequency, then if I'm delayed by a specific amount of time, I will be delayed by a greater phase than I would be if I was just working with a small frequency. Okay? Now, moving forwards, we're just going to start talking about filter structures. Okay? And I guess how to add a little bit of intuition into constructing them. So, first up, we have direct form 1. Direct form 1 goes ahead and takes we're actually going to divide this into 2 sections. The first section is all to do with x, okay? And something to note is that when we have our transfer functions, let's just consider h of z. H of z typically equals to a0 plus a1z inverse plus yada yada on b0 plus, actually, usually this is 1, plus b1 z inverse plus so forth. To characterize our z transform, this corresponds to a difference equation of the form yn is equal to the summation of a k z to the minus ak x n minus k plus a summation of bk y n minus k. Okay? Alright, so given this, these are how we typically map between the two, okay? And we would have a negative there. Alright, so with this in mind, everything to do with x gets shifted to the numerator and gives us our zeros, okay? And so we can consider this left-hand side of our structure to be the zeros, okay? So when we try and analyze this a little bit deeper, we end up with 2 transfer functions, p of z and q of z, whose multiplication gives us h of z, okay, which is our proper transfer function between y and x, okay? And likewise, by defining things this way, we observe the poles are given purely by the y coefficients. So this section over here relates purely to the poles, okay? Now, to recognize the usefulness of this manner of expression, we can go ahead and actually move things around. And we'll notice that when converting between direct form 1, direct form 2, and the canonical form, we actually see that all we do is we keep the exact same transfer functions. We just shift things around. And so in this instance, we deal with zeros second and poles first. All right? And then in which case, we're able to join our delays together because they're all in the same place, essentially. Just a second. Never mind, I just think the camera might be frozen. No worries. Okay. So that is direct form 2 and canonical form. Now, the pure definition of canonical form is just requiring the minimum number of delays within the circuit, within the filter structure, okay? So if you're able to do that in any direct form on its own, perfect, you already have the canonical form, but when we're dealing with anything a bit more convoluted, canonical form becomes a bit more profound. Anyways, parallel form, we get the summation of different transfer functions, which it can be very useful, for breaking our circuit down into lots of smaller, more manageable circuits and such. And the way that we typically describe these is by having partial fractions divide our bigger transfer function into lots of smaller transfer functions. Okay? So we'll just make a little note there. All right. Next up, we have our magnitude responses. Well, frequency responses. We'll always note that magnitude response should be an even function, and phase responses will always be odd functions, with discontinuities, potentially whenever you want to jump by a factor of 2 pi. We note it in different ways, and it is very important to recognize that we are just taking our function within the z domain, replacing z with the unit circle, so e to the I theta, and then observing that rotate. Okay, and so the notation of h of theta is really just replacing z with e to the I theta. Yeah. All right. Now we'll start talking about minimum, maximum, and mixed phase filters. So ideally, what you can do is replace all zeros that you have with the reciprocal, okay? And by replacing with the reciprocal, you don't actually impact the magnitude response at all, which can be very useful. The phase difference that you observe can then be characterized in terms of minimum and maximum phase responses, in which cases we can actually put a reason to this. If all of your poles and zeros are within the unit circle, you'll observe a minimum phase response, and if all the zeros are outside of the circle, you will observe a maximum phase response. So in terms of minimum and maximum, it is really just talking about how usually within frequency responses, we have our 3 major points being 0, minus pi, and pi. A minimum phase response will go something like this. So I'll just min. A maximum phase response will likely go like this. And then you have mixed ones in between. All right? Fantastic. And then this brings us to the concept of all-pass filters. By recognizing that having zeros replaced with their reciprocals, our magnitude response remains the same, what we can consider is functions where they have poles and zeros within the same manners of regions. Where you actually replace all poles with you have all your poles be equal to reciprocals of existing zeros. Okay? All right. And I guess that concludes section 3 in terms of digital filter design. Sorry, no, not digital filter design, digital filter fundamentals, and we'll be moving into digital resonator fundamentals. Typically, we're dealing with second-order digital resonators, and that begins moving into notch filters, the stability triangle, and digital oscillators. Okay, it's not a very large section, but it has its fair bit of content. So, just, I guess, moving straight into it, we have second-order digital resonators are given by having their zeros at z equals 0, so the zero inducing minima is all around the circle, so best way to think of this is in our pole and zero choosing method, where we get the unit circle, and we go ahead and we say, okay, well, if I'm defining this as an angle of 0 degrees, this up here is going to be 90 degrees, up here, pi, whatever, then by defining my digital frequency response or analysis, I can pick which parts of the circle correspond to different frequencies that I'm sampling with, okay? And just putting into analysis. And so, by having a 0 at 0, so I'll put an open circle there, by having 0 at 0, you effectively enforce a 0 action against all frequencies, if that makes sense. Because zeros go ahead and try to pull it downwards, okay, to give you minimum. Whereas a pole goes ahead and tries to bring it up to infinity, okay? And that can be particularly seen in magnitude responses. Anyways, just getting back to the point, second order digital resonators, we go ahead, place the zeros at 0, and the poles at RE to the J theta 0, and RE to the minus J theta 0. This will be a stable resonator when R is less than 1. It'll just have a gradual decay. You can make it an oscillator by making this equal to 1, but anyways. It will always have a transfer function of this form, and I guess the biggest things to consider, I made a little mistake up here, that should have been to the minus 2. I mean, it doesn't have to be minus 2, that just puts a delay, but anyways, it can be. The reason this is so profound is because now we know specifically what do our B values look like, all right? And so, by using this generalized term, we can go ahead and define certain values, such as your gain as well as your bandwidth, in terms of your radius that you provide, as well as the angle at which you're implementing the resonator. All right? So moving forwards, notch filters really play on this concept of using the unit circle. And so we place zeros for minima within certain frequency areas, and then poles for maxima within certain frequency areas. And the greatest way to think of this, I'll just draw another circle. We're going to be drawing quite a few circles today. In fact, to save a little bit of time, I'm going to copy it for later. So, we have our circle here. If we go ahead and we place a pole right on the unit circle, and maybe a 0 in the center, what we'll observe within our frequency response is going to be, okay, it'll attenuate downwards typically within certain regions, but when we hit this angle that we specify here, it will go ahead and shoot upwards, okay? Otherwise, attenuating back downwards. And then repeating every 2 pi, all right? So in this essence, we can choose where we put our poles, choose where we put our zeros, and therefore kind of push our function together the way we want it to. As that was a pretty simple example, I'll go ahead and just make another. So let's say we want our frequency response to go ahead and look something of the form this, okay? Having this as 2 pi, all right? So in this instance, we want zeros at both 0 and pi. So we go ahead, we put zeros there. But also, we want to have a raising directly in between, okay? And to really implement this to our best ability, there are a couple things we could do. We could just put our poles directly in the middle, but if we want to emphasize it a little bit more, we can raise them a bit. Okay? And what we observe here within our magnitude response between 0 and 2 pi is really just, we can have a pole that would make it more of a cusp, or you can have it closer to 0, in which case it becomes more rounded. Okay? So that's that. That's the kind of intuition we want to build. All right, so moving forwards, we have the second order stability triangle. So just understanding that stability is where all of our poles of certain magnitudes lie within a certain unit circle, okay? And the condition for it lying within this unit circle is given by this triangle, okay? Especially for B1 and B2 when we're only dealing with them, okay? So let's just color in the circle a little bit, sorry, triangle. And yeah, so just by recognizing that your coefficients lie within that triangle, we can very easily identify that, okay, within certain regions, we're going to have barely stable, where it turns into an oscillator, and then truly stable, where it's just a resonator, okay? So just a little bit more on oscillators. If you have a pole on the circle, that means radius is 1 now. You have a proper 2 here rather than 2r. And since it has a radius of 1 and it is unstable within that manner, it means that if you supply any kind of excitation to it, it'll just keep on going. It will self-sustain itself, okay? All right. I guess that's all we have on digital resonator fundamentals, and so we'll move on to digital filter design. So the little fun thing with this is within the slides we get a lot of information on how we would transform a lot of these analog filters into certain other analog filters with certain transformations. It's not the most relevant to us within digital signal processing. It gives us a good, I guess, analog to work with, and how we might relate it to actually constructing circuits. But for the sake of understanding, it is just all about these manners of transformations, which we will cover within digital filter transformation. All right. So we use it to recognize certain methods we would use. Anyways, we're going to jump pretty much straight into where we deal with digital filter designing. And so let's think about FIR filters first. The method we're going to consider just this time, instead of listing through all of the possible ones, will be the windowing action. And it acts as a manner of truncation from a IIR filter. So windowing, typically, you would go ahead and you would just define it as a sequence of impulses and then multiply that with whatever signal or filter you're dealing with. Okay? FIR filter design can be in a method produced by working around an IIR filter you've obtained and then truncating it, as we saw it within the assignment, and can be a very useful tool to ensure that data sizes that we're dealing with are very restricted, okay, for storage purposes. Anyways, this becomes even more useful when we recognize that the digital frequency analysis of it just becomes a geometric sum, in which case we can deal with it rather nicer. Anyways, enough of that. We're going to just keep on moving to the more interesting IIR filter design given by the impulse invariant method. Okay, so the impulse invariant method, it is a little bit intuitive. It goes ahead and says, okay, if I have some manner of response right here as my signal, I will just sample that and then perform a Z transform on it. It's a little bit intuitive, but I guess in a certain sense, there are different ways you can do this. So, and I guess that starts moving into content within chapter 6, where we talk about multi-rate systems and a specific chunk of multi-rate systems. But that is essentially all you do to it, to transform it into some manner of function. All right. Digital filter transformation. We mentioned before, we don't really need to look at the analog filter stuff in too much depth. It's more of an analog to our digital. And so we'll just look at how we can transform some manner of low-pass filter, more namely a low-pass filter with a unity gain and a bandwidth of theta p, which I'll just underline. In other words, that is its cutoff frequency. We can actually transform this into another low-pass filter with a different bandwidth or cutoff frequency, with the transformation of Z inverse into Z inverse minus alpha over 1 minus alpha Z inverse. All right? And just moving forwards with this, we have all of these transformations defined between low pass, high pass, band pass, and band stop. Yeah, there's not too much to consider here. It is all about just certain filter transformations that we can apply to transform different values to other values. There's not too much to deliberate on. And I guess that brings us into chapter 6. All right, so chapter 6, we're dealing with multi-rate systems. All right, so multi-rate systems, we are entirely talking about the instances where we may potentially be working with, okay, I have system 1, it samples at, let's say, 5 hertz. Fantastic. So this will just be number 1. We'll make number 2. Let's say it works at 20 hertz. However many that is. And we'll have system 3 working at 4 hertz. Okay? All right? So we want to potentially use data from all 3 of these in conjunction. And how could we do that? Well, the easiest way that we might believe so is, okay, if we're just going to consider number 1 and number 2, we would just either downsample number 2 or upsample number 1. So let's just define what we're talking about. So we have upsampling and downsampling. Downsampling is typically referring to decimation. Decimation is where you just take the nth sample in every set, okay? And so by taking the nth sample, I can decimate by a factor of 4 in this instance and just grab every 4th one, okay? In which case, it reduces this to 5 hertz, okay? In essence. Nothing too fancy with it, but that's that. Next up, we have interpolation, which is where we insert samples between every sample, okay? And so this is called upsampling. And it is important to note that it is only doable in each step by integer factors, okay? Just on the basis level. So we can put our, we can decimate by destroying samples in between, and we can interpolate by introducing new samples, okay? Now the tricky bit with interpolation is that we actually have to give values to those introduced samples. So let's just try and think about how we would do this. If, again, we want to work between number 1 and number 2, we would go ahead and we want it to be, okay, 20 hertz. We need to interpolate by an integer factor of 4, or upsample by a factor of 4, right? And so, first things we would do is we would add, every sample needs to turn to 4. We would add 3 samples per sample. So we add 3, but we think to ourselves, okay, it doesn't look quite right just yet. Okay, it doesn't look like the signal it was before. We would want some manner of low-pass filter or frequency response to recognize that this is the manner of shape we want the signal to take, right? And if this is the manner of signal we want it to take, we need to raise those points as such. Now, there are a couple ways we could do this. The first way would be through windowing, where we go ahead and perform an averaging window. One such example is given by the linear interpolation model, where we interpolate by a factor of 2. And so we just multiply our new upsampled sample by, we convolute it with this manner of signal, okay? And what that would do is it would go ahead and say, okay, every second one is going to stay the same, but the ones in between will get a manner of averaging between the two. Okay, so you'll end up with pretty much a polygonally joined set. Okay, and then it will join your values between it. However, there is another way we can do this. I guess a nicer way. And the way we do it is by passing in these inputs, but into a low-pass filter. Okay, and so if we generate it as such, and we pass it through a low-pass filter, it will think to itself, okay, what is this thing made up of? Initially, we had something of this shape. Something of this shape. And so when I think about low frequencies, or low frequency signals, I have to think about, okay, what manner of smooth curve fits it, okay? And that's what a low-pass filter will emphasize. None of the, I guess, high-frequency stuff that would be characteristic of it immediately dropping to 0. So by applying this manner of understanding to a newly interpolated sampling, we can go ahead, erase whatever high-frequency noise stuff it believes is bringing it back down to 0, and only keep what would make it smooth, okay? And so that is called a low-pass filter interpolation. And typically, what you would do is you do the interpolation process. I'll just draw it as a diagram. X goes into a box, interpolate, goes into another box, which would just be a low-pass filter. And then if you want it back again as X, we would decimate. It's a very cool word to use. And we'd get X back out, okay? That's just how we would go through things. All right, so that is decimation and interpolation pretty much covered, and especially within the cases of 1 and 2. But what if we want to deal with number 3? Okay, let's say we want some manner of joining between 1 and 3. We see that they're not integer multiples of each other. We have a definite problem. However, we can very easily work with the number 20. Okay, number 20 is a lot more intuitive because it is a multiple of both 4 and 5. So things we could do is we recognize we can run around almost in a vector method, run around 220 and come about to 4 with decimation. So very similar to this kind of model we've just proposed, we can chuck it through both interpolation and then decimation to get a factor multiple of our frequency, factor multiple of our sampling frequency, okay? And so, in this case, we can upsample to 20 and then decimate to 4, in which case it would go to 4, okay? So we bring it to 20, bring it to 4. All right, fantastic stuff. And I guess as a final note on the course content, we have modulation within the syllabus. There's not too much spoken about it. It's just an extra thing that we can consider, especially within digital signal processing. And all it really does is it goes to our Fourier transform. Typically, we just get x of theta, but it goes ahead and splits it up onto two sides, okay, against some modulated frequency. And so the way it would look, just typically, is let's say we have, here is big X of theta, and big X of theta just looks like a box, in which case it's just 1 between this region. It's the sum of 2 step functions, nothing too deep. If we go ahead and consider, okay, xn cos theta 0 n, what it would instead give us within a Fourier transform would be the same box split in half and then pushed away from each other with an angle of theta 2 times theta 0, okay? Where your center frequency would still be theta. Actually, I'll denote this theta 1. All right. So important to note, it splits the amplitudes in half. But yeah, it's a pretty cool thing and has future applications. All right. So look at us. Within 55 minutes, we've covered the course's content. All right. Fantastic. Bloody good job, guys. Now, what we'll do is we'll just go ahead. We will examine just what does the final paper, what are the rules behind the final paper, how do we try and maximize marks in it. Then we'll do a couple practice questions from the sample paper, and then we'll jump onto a bit of a Kahoot at the end for anyone who has recently joined. So let us keep on cracking. So things to note, this final does have a fair bit of weight behind it, but we do get what you might say sufficient time to answer 4 questions, okay? The biggest crux of this exam and this course is the TLT structure. So as a tiered learning taxonomy, AMBI has given everyone the option to put in as much effort as they feel, and so marks are split accordingly. So what we urge you to do is ensure that you read all the questions first. You can work in a top-down approach to see, okay, here are the questions with the most weighting. Let's work down from there. Potentially, this is something I can do. Does it fit the time? And it's really important because when you look at TLT5 in respect to TLT2, it is twice the weighting. So if you think you can do a TLT5 question within the time it takes you to do 2 TLT2 questions, that's just fantastic. But it is very important to note that given your responses, only your top 4 questions will be marked, essentially, okay? So you can go ahead and do all of the second level questions if you feel like it, and then move on to do more questions, but then fewer TLT level 2 questions will actually count towards your mark. It is a safe way to play it. However, we just have to think about what we can do and what we can do in that time. Okay? So something very important to note. There's nothing too extra specific about this. We may be given notes. I'm not too sure. It is something for AMBI to deliberate on. But yeah. So, just important stuff, recognizing that this is the marking scheme of the exam, as we may have noticed within the assignment structure. So, do your best, guys. Just make sure that you are being, I guess, a bit wary of the fact that total marks are capped in certain regions, and only 4 questions are marked. Okay, you can play it safe, and that is perfectly fine. by doing more questions, just as long as you're comfortable. Anyways, we have the sample paper. All right, so here's our sample paper. We'll be going through a couple of questions with a worked solution. So the first question we'll look at will be question 3 of TLT 2. All right, so just to remind everyone, feel free to ask questions during the seminar. More than happy to clarify things. So, question 3, we want to design a notch filter, HZ, with a notch frequency of 60 Hz, a stop band of 5 Hz, and bandwidth. Stop band 5 Hz as its bandwidth, and sampling frequency of 300 Hz. So, I guess we can start converting things in here. If you have a sampling frequency of 300 Hz, 0 to 300 is the same as 0 to 2 pi. This is just on frequency. This is on our digital. And so we convert it accordingly. 300 goes to 2 pi. Okay, so divide by 300, multiply by 2 pi is how we're going to convert. Notch frequency of 60 Hertz is a fifth of this guy. So you think, okay, 2 pi on 5. Fantastic. A stop band of 5 Hertz, well, that is going to be equal to a sixtieth of your bandwidth, and so you get pi on 30. Okay, so that's just us converting into digital frequency. Now we're going to actually start designing it. Now, I guess the biggest reason we want to deal with it in this method is the fact that I believe there might be a small mistake within the sample solutions for this question, which was very well spotted by our fellow academics director, Jackson Hood. So we will go ahead and think about this. When we're designing a notch filter, we're going to consider pole placement, zero placement, right? So especially for a notch filter with a stop band, we want to consider something that looks like this within our frequency response, okay? Sorry, within our magnitude response, where we get a stop band. This corresponds to 5 Hertz, and the stop frequency corresponds to 60 Hertz. All right? So, first things first, we place zeros at the notch frequency. So, reconsider our digital, our unit circle. That's the one. We go ahead, 2 pi on 5. 2 pi on 5 is a bit more than that, than pi on 2. So it's going to be hereabouts, where we go ahead and we have to place zeros, because we bring it down to form a minima. And then, since it is actually hitting the 0, we place that on the actual edge of the circle. Okay. Next up, poles also at the notch frequency, but with R determined by this function. So here we go, and we determine that the pole plots will have radiuses of 0.9476. Okay, so it'll be very close, very, very close to where they are on there. Okay, in fact, I'll just do them in red so we can see. Fantastic. So this actually gives us the solution immediately. And to clarify things, Jackson did an extra MATLAB plot where bada bim, bada bam, it was fantastic. And we just have to note that the MATLAB plot of the proposed solution within the document was a little lacking. But nevertheless, we go ahead and move forwards. Fantastic stuff. All right, so to go ahead and construct the transfer function, we just put these poles and zeros together, and we can, if we really feel like it, ensure that it has a unity gain of 1 by just plugging in, okay, well, when we get an angle of 0, or in other words, z is equal to 1, do we get what we want? In which case, we'll just multiply it by certain coefficients. So when z is 1, we just go ahead, if this is A0, A1, A2, B0, B1, B2, we would multiply this by B0 plus B1 plus B2 over A0 plus A1 plus A2 to ensure that there is unity gain at that point, okay? Just as a little bonus thing to think about. All right, fantastic stuff. Let's move on and think a little bit more about the second part of that question. So, we've gone ahead and designed it. Fantastic. We've gone ahead and drawn, we need to go ahead and draw an implementation, okay? So that requires us to create a block diagram, okay? Implementation means block diagram. So I'll just write that down real quick. So implementation, this means a block diagram. And so, given that it is a fairly simple transfer function, we just need to deal with between 2 and 4 delays, and so on. Now, it doesn't reference a specific type of implementation, so we can just draw it as such, where we multiply it down from the output, we delay it from the output and input, and then just sum it together within the middle, okay? In which case, this is direct form 1, and there's not too much to really consider. We just remember we got poles on one side and zeros on the other within those transfer functions, okay? Great stuff. All right, now we go ahead and we think about section B. Determine the transfer function hz of a discrete time signal with a pole zero map shown in this figure. Now, we recognize that there are poles on the imaginary axis, meaning at pi on 2 and 3 pi on 2, rather at pi on 2, we're going to want a peak. Okay, that's where our maximum is going to lie. And since we have zeros pretty much on the unit circle at the angle of 3 pi on 4, we're going to hit 0 when we get there. So just by a preliminary analysis, we can recognize, do I still have the circle? Bloody fantastic. All right, we have poles there, digits there, and when we build it, since this is where our zeros are, we're going to get a 0 just down here. No, this is going to be up to pi 0. This one will be 3 pi on 4. And so, just by the way, so we know we're only going 0 to pi because we understand that the magnitude response is an even function. So in other words, it would be mirrored on the other side. And we also know it's periodic, okay? So nothing too much to consider there. And a pole at pi on 2. All right, so what we're expecting is going to be something of the form like this, okay? Something like this. So we can actually go ahead and perform it more rigorously by chucking it through a proper analysis, okay? So by having that in our head, we can go ahead and create the transfer function, all right? So transfer function, we already know the poles, we already know the zeros, we combine it all together, and we are dandy. All right. So that's that. Okay. Next up, we're going to look at the third part of the question. Fantastic. We're going to write the equation for the 4-point digital Fourier transform, hk, of the impulse response of a filter given by hn equals 1, 2, 3. And we want to determine as well what the DC gain of the filter is. Okay, so DC gain, that's just when your frequency is 0. So you plug in z equals 0. Sorry, z equals 1. My bad. All right, so let's go ahead and do it. So let's just recall digital Fourier transform formula is given by xk is equal to the summation from 0 to n minus 1 of xn e to the minus j n 2 pi k on big N. Now, just to remember, as our digital Fourier transform is a periodic function, it is something we need to consider that it is only between 0 and n minus 1. Well, big N minus 1, n is your period number. And let's just keep on moving. So, given that it is a 4-point DFT, we just need to do n is equal to 4. We plug in our function hn, we perform it, and we get 3 of them. Okay? And that is just about it for that section. But we'll go ahead and determine the DC gain as well. All right? So here is the hk given by it. And then we sub in 0 for the value. Sorry, 0 for the k value. So this goes to 0, this goes to 0, the entire exponents go to 0, and we only really need to consider the summation here. All right. So we have it. Yep, so given that it's a 4-point DFT, we recognize we only really had 3 points to begin with, so we pad it with a 0. And since we padded it with a 0, we still recognize that the sum, this only really goes from 0 to 2. Okay? So when we chuck in a 0, we have the sum has n is 0, so we're just taking the 1 first up. We end up taking the 2. And when we plug in a 3, we get this side, okay? So 1 plus 2 plus 3, oops. We have a DC gain of 6, all right? That's that. All right. Nice. So moving forwards, next question we're going to look at is going to be question 4, still within TLT 2. So here we go. Question 4, let's just read it. A signal with a bandwidth of 0 to 3 kilohertz has been sampled at 8 kilohertz. And for a particular application of this signal, this signal is required to be used at an increased sampling rate of 18 kilohertz. Draw a block diagram to show how you would efficiently implement a system to achieve this, indicating the type of digital filter you would use, and give reasons. Wow, this sounds like something we were talking about before. Let's go ahead and take a gander. So, Lovely stuff. We want 8 to go up to 18, and so the kind of factor we want to multiply it by is 18 on 8, which is equal to 9 on 4. So we want to perform a decimation here and a interpolation here. All right? So first things first, always interpolate. We interpolate so that we retain as much information as we possibly can. All right? So doing so, we get 72 kilohertz. Now we use a digital low-pass filter. Okay? By using a digital low-pass filter, just to remind everyone what it looks like, a digital low-pass filter is a block diagram. Okay? The block diagram, sorry, not block diagrams, we called something else, but it is a blockular diagram where we only pass, quite literally, all the frequencies until the specific stop frequency. Okay? And we would want to fit this such that it would only fit the frequencies that could originally fit within the 8 kilohertz input. Okay? And so if I were to actually think about this really hard, we have 0 to 72 kilohertz. This gets converted into 0 to 2 pi. So we're dividing by 36 and then timesing by pi. All right? When we chuck in 8 kilohertz over here, well, really we only want to preserve 4 kilohertz since that's what it's going to be between 0 and pi. We want to preserve this up to 4 pi on 36 or just pi on 9. Okay? And so that's how we could describe it. Fantastic stuff. So we do that. So that's just a little bit of extra information that we could give to the digital low-pass filter. And then we decimate it by dividing by 4. And so we just take the 4th sample. Good stuff. All right. So, I think I missed out on one little slide in interpolation and decimation, which actually makes this all the more better when we consider it. So let's scroll up. Here we are, these two little cat ears. The thing is, if we have the frequency response of this and we perform a decimation, ideally what's going to happen is it's going to go ahead and, mind you, typically our frequency analysis only goes between 0 and pi. This is just the mirroring that you would see to make it periodic and symmetric. It goes ahead and it clips it off up to the point of decimation. And so it would bring the cat ears together. And interpolation ideally would do the opposite. So something to, I guess, recognize is usually what you might potentially suffer from when you interpolate is getting something like this. And so to remove that kind of signal, you would chuck in the low-pass filter, which would multiply it by 1s within the specified region and 0s elsewhere. So that would remove this middle bit of symmetry. All right? So that's that little bonus bit of knowledge that we really needed on that section. And so we'll just keep on moving. So let's do this. We were at question 4, and we just up and down sampled it. Now we need to calculate the minimum cutoff frequency of the digital low-pass filter. Oh, whoops. I already did that. Got a little ahead of myself. Let's double check with the working. And so we were talking about, here is the thing we were using back there. But we have to think a little harder. So before I mentioned pi on 9, this is going to be within the 72 kilohertz. And that translates nicely down to the 9 kilohertz region within 18 kilohertz. So that's the reason we would have passed that through there. So just something we could have noted. All right. Yep. So we still only use that, but there's a special thing. There's a bit of information in the question that we haven't used just yet, and so we have to be rather careful. Now note that the signal has a bandwidth of 0 to 3 kilohertz. So the bandwidth spans from 0 to 3 kilohertz. Okay? And so when we describe our initial function, we only really we see whatever, and then it hits, this would be pi, and this would be our 3 kilohertz region, which would be 3 pi on 4. Okay? So just before we've hit pi, we go ahead and say, okay, this is where the bandwidth spans between. Okay? Here's our 3 dB point. So what we could do, additionally, would be destroy this section after the little bit of working. So we could limit it to 3 kilohertz still. Okay? In which case, this pi on 9 would instead be a different value. It would still be, I think 3 kilohertz. Let me double check. Yeah, so the signal itself was only at 3 kilohertz. So we only really need to analyze that kind of section. Okay, that's the minimum thing you could use. Moving forwards, there's question B. A signal xn has a spectrum of x theta as shown. So it's this little triangular thing that goes to 2 pi on 3. Fantastic stuff. The signal xn is applied to the system shown below. So we have an upsampling of 3. We apply some manner of filter, and then we have a decimation of factor 2. Okay? So the ideal low-pass filter, Hz with a gain factor of 1 within the passband and a cutoff frequency of theta equals pi on 3. Let's do this. So, first things first, we already have magnitude spectrum of x theta. We're going to upsample it to see what happens, and then we're going to move forwards. So, let's not skip ahead too far. Hold up. I might be a little blind. I think there might have been a little mistake just with this one. But anyways, nonetheless, let us think about it. So, the way we would go about this manner of question would be, first things first. We interpolate. Oh. There we go. We have our original magnitude spectrum right here. Fantastic stuff. We go ahead and we interpolate. And so all that means is, originally we had, the cat ears, lovely stuff. Now, interpolation is introducing more samples, and so it should go ahead. We take a look at the notes. Interpolation should push them further apart, and so the cat ears will be extended further apart. All right. Next up, we'd go ahead and apply the gain pass filter between 0 and pi on 3. Now note, since it is pi on 3 and we've interpolated it, it really doesn't do all that much. So beforehand, it goes up to 0, 2 pi on 3. Pi would be sitting just very close to it, so it actually looks something like this. Pi 4 pi on 3, 2 pi. We multiply by a factor of 3, so in other words, everything gets 3 times thinner. So 2 pi still over there. This gets a third thinner, so that's 2 pi on 9, which, oh my gosh, it's just within the band of pi on 3. Fantastic stuff. So by having this Hz pass through here, we recognize that everything is conserved just because the frequency response of our signal is just clipped off at the point just before anything gets lost. Okay? Fantastic stuff. It's the same. Then we see yn, we down factor by a factor of 2, so our cat ears move closer together. So 0 now to 4 pi on 9, which is so close to pi on 2. We get that. This is going to be pi, and then all the way over here will be the other cat ear. Fantastic stuff. All right. We happy with that question? All right, lovely. I think what we're going to do, I see. So B was skipped and moved straight on to C. Let's have a read through C, then a quick go at the level 3 question, and then we'll move on to the Kahoot. Okay? So using the following difference equation, you're required to implement a digital oscillator that generates a sinusoid. Choose the appropriate initial conditions, and note that xn is the input, yn is the output, r is a constant, and you're required to choose an appropriate value for r to sustain oscillation, which most typically is going to be about 1, but we'll take a gander. So we move on to C. Yep. Okay, so R is 1, is an oscillator, fantastic stuff, we remembered that. And now, using the difference equation, we need to make a thingy. So, we go ahead, restructure it into what we could say would be a transfer function. We know that all of our delays are actually just going to be in terms of y. Everything's in terms of y. That's crazy. And so we don't need to think about n all that much. What we could do is have the initial condition on y, and then we just exclude x all entirely. Okay? So having xn be equal to 0, we don't need to think about it. And so we just generate the whole section, since we're dealing with feedback, and we just need to supply the initial conditions. So we supply 2 different initial conditions, simply because it is of degree 2, going backwards, and so we give 0 and minus sine theta 0. Fantastic stuff. All right, move on to TLT level 3, and then we'll jump onto a couple Kahoot questions. All right, let's do this. So, question 3, we got part A, the frequency response HD, that's funny, of theta of a linear phase FIR filter is given by HD theta equals e to the minus j3 theta, given that 0 is less than or equal to the magnitude of theta is less than or equal to pi on 2, and 0 elsewhere. Okay, so this is the information given, and it is a linear phase FIR filter. Okay, so just remembering how linear phase works, it means it is symmetrical, right? Coefficients are symmetrical. So we go ahead, we think about this, and we need to show that the impulse response is given by this exactly. So we're given the transfer function. Sorry. Yeah, we're given the frequency response. Okay. We now need to determine Hn. So let's go ahead and do it. They gave us the transformed one. Now we need to apply the inverse of it to obtain our discrete time signal. Okay, so we apply discrete time Fourier transform, and we obtain xn. Okay, so once again, we're just applying the integral. We recognize the bounds used on this integral, so we no longer use minus pi to pi, minus pi on 2 to pi on 2. Okay, sub it in. Oh my gosh, the exponent joined together and factors out. Lovely stuff. And so we actually get left with a very, very nice sine equation right here, giving us that hd of n is equal to 1 on pi n minus 3 times sine of pi on 2 times n minus 3. All right, lovely stuff. And that was as required. Fantastic. All right, part II, the length of the impulse response of this linear phase filter is set to 7. Find the values of the FIR filter coefficients using a rectangular window function. Oh my gosh, let's do this. So typically, okay, just recognize rectangular window function. We're going to go ahead and just sum up the first 7. Okay, now note, yes, we have symmetrical coefficients. Mind you, symmetrical in the sense that it is conjugate symmetry, so if we get any imaginary numbers, it works together. And so we only really need to consider, since it is 7 samples, we center it at 3. And it actually works out as required. Lovely stuff. All right, let's keep on going. Half an hour to go. I will try and make sure we fit in the Kahoot on time. But nonetheless, we're going to sketch the phase response of the system. Okay, so we had the magnitude response. We were able to work backwards from that to be able to get the coefficients just on their own in the time domain. And now we're going to bring it back to get the phase. So, phase stuff, it gave us frequency response, so we could kind of work around that. Since we had e to the minus j 3 theta, we kind of look right up here, and there it is, minus 3 theta. Lovely stuff. But then it cuts off to 0. Okay? And so here we have it. You apply the same gradient, and you recognize cutoffs to keep it bounded between pi and minus pi. Lovely stuff. Question B. We're going to use the bilinear transform to transform an IIR digital low-pass filter based on a prototype normalized function, GS. And yeah, the digital filter is designed to operate at a sampling rate of 8 kilohertz with a 3 dB cutoff at 2 kilohertz. We're going to show that G reduces this to z plus 1 all squared over 3z squared plus 1 over 3. So what we're doing here is, with a bilinear transformation, as we mentioned in a couple of our filter transformations just earlier, we're going to go ahead and we're going to apply a manner of transformation. Okay? And so with that in mind, we give it just a second. Just so you guys know, I can see the stream just on here, and I'm certain that the camera has frozen. In fact, I'll just do a quick audio check. Never mind. All right. Okay. So let's keep on moving. we apply the transformation, and then what we're going to do is draw an implementation as a cascaded structure. Okay, so here we are. We are going to be performing the transformation. We recognize that we want, what type of thing did we want? Sorry. Has a cutoff frequency there. It looks like low pass filter. Okay, so something we got to do is we go over here and we work with warping. Okay, so just understanding that S and all, when we convert from S to Z, our conversion is typically using the sine inverse function. And so between about pi on 4 and minus pi on 4, it works perfectly in one direction, and the other works rather linearly. However, when we start going towards pi on 2, everything gets squished. Okay, that's just what warping means. So we're going to apply pre-warping by understanding that within certain ranges, the tan needs to be considered. Okay, so right over here, we're just considering what is the range at which we are dealing with our cutoff frequency. Okay, so denormalizing, we convert S into S on omega t, since this is a just pretty much scaling to pre-warp, and then we're going to perform the low-pass filter transformation. Okay, so we do so. We get a bit of a mess, but we work through it. Fantastic stuff. And we obtain this. Now note, when dealing with things of this form, something that we can do is put it in Z inverse form, which would look something like 1 plus 2 Z inverse plus Z minus 2 on 3 Z minus 2, 3, 1 plus a third of Z minus 2. All right, lovely stuff. Next up, we go ahead and we need to convert this into the cascaded structure. Cascade just means one and then the other. So direct form should be applicable. Lovely stuff. So here we have our zeros, here we have our poles, and so coefficients are just given as required. All right, that pretty much brings us to the end of this content. Lovely stuff. Good luck with that stuff, and good luck with the rest of the sample paper, guys. We are going to hand over the question section to our ELSOC Vice Pres, Sophia. Give her a little... Yeah, okay. So, while we do this, don't peek. It's going to be question by question, and we will actually go ahead and format this into a Kahoot. So, what you might have heard beforehand were these noises. Let's hope my device can handle it, and let's get moving.
Lovely.
Right.
Okay, that was so good. Thanks, Otto. I personally learned a lot from that. Okay, I guess we'll wait for players first. Thanks. Okay. Second mode. Oh, wait, you have the banner back?
Yeah, I took it.
Fabulous. Because someone stole it last night.
Cool.
Yeah.
I mean, it was in the box.
Anyways, yes. Oh. See. Better get 100%. Jackson Hood.
Yeah, we gotta wait.
Lovely.
In the interest of just keeping the stream stuff relevant. Okay, for everyone online, we'll just be pausing the stream now to ensure relevance. Alright, see you guys, good luck with the rest.